Good afternoon, everyone. So I'll start with a disclaimer. The disclaimer is that I'm only 9 months old in blockchains. And then I'll be talking only about blockchains without Bitcoin. So I will not be talking about digital currencies. So any questions that you have on Bitcoin or on digital currencies, please postpone them until Professor Venu Madhavan completes his lecture. So here is an outline of my talk today. So we'll have a little introduction. Then we'll talk about the blockchain data structure. Then I think there are a few things which are very important to know when we talk about blockchains. So we'll take a random walk of some things to know. Then we'll look at some applications. So the title contains industrial and societal applications, so I will try to give such applications. Then some of the work that we have done in the last 6 months on designing a trusted B2B platform, which is blockchain based and which also uses game theory, is what I'm going to cover. Then we are primarily interested in blockchains because of our interest in game theory. So I will see whether I can spend some time on saying a few things about blockchains and game theory. And finally, I think we'll take a reality check on the blockchain technology itself. There is a lot of hype about blockchains that is very well shown by the number of people who are attending today's talk. I hope that during this 45-minute talk, I will be able to say some technical reasons why this hype is really not a hype. It is something real. So it's not a buzzword anymore. So in 2008, the Bitcoin paper was written by Satoshi Nakamoto. It's a very simple 8-page paper, a must read for everyone. You can actually finish reading it in exactly 1 hour. Simple but very, very powerful ideas. Now there are several hundreds of startups in this area, more than 30 in India itself. Probably that number is even more. So much of venture capital has been sunk into this area now. And Praful Chandra, who finished PhD from the game theory lab, on the day of his Viva, he said, I'm not going to do any more game theory, enough of game theory. And he said, I'm going to have a startup on blockchains. And he actually has a very interesting blockchain startup called Coin Earth. And substantial sums of money are being invested by governments, financial institutions, banks, and so on. I think in some way, blockchain technology is actually like TCP/IP. So that's a question that I'm posing. We will see why I would like to say that blockchain technology is like TCP/IP. So TCP/IP as a technology, it arose in 1972. And then it has taken about 30 to 40 years for the full power of TCP/IP to be realized. So perhaps blockchain technology is also something like TCP/IP. So let me start with a very simple example. There are property titles with which we are all very familiar. Turns out that if you take statistics about the number of property titles which are not trustworthy in the national context, in the Indian context, it's as much as 70%. And as you know, titles and documents can be fabricated, manipulated, and so on. And of course, in Bangalore, there are a number of such cases. And there are umpteen number of layouts in Bangalore which are in trouble, all the way from Banashankari 3rd stage to Banashankari 6th stage, including Malleshwaram and so on. And our chief minister makes this following statement: we will not spare officers who perpetrated this fraud and collusion with land mafia. The drive will continue, and so on. Okay, so this is as far as land records go, and the umpteen number of problems we have with land records. Now, one can ask the question, what if these records were immutable, cannot be changed at all, and they're available in a distributed public ledger for everybody to see these land records, and all these records are added in a highly secure and authenticated fashion, and there are no trusted third parties involved here. In the state of Karnataka, there is a project called the Bhumi project, and it's a project with very lofty goals. This project, has created a database of title deeds, and it has served its purpose. However, it turns out that if you want to access anything that is in the database of Bhumi, it's almost next to impossible. It's highly centralized. It is not available for anybody to see, and I think it is also highly manipulable. So if these records were immutable, available in a secure fashion to almost everybody who is interested in this, and there are no trusted third parties involved here, I think the situation will be completely different. And this is precisely the reason why the blockchain technology could turn out to be a game changer for some of these societal applications. Now, there is a lot of interest and action in India at the present time. There was a white paper that was released by the Reserve Bank of India in January 2017, and so these were the kind of transactions that the Reserve Bank of India stated that can benefit from blockchain technology. And if you look at some of the recent headlines, all the way from November 20th, when State Bank of India said they will use the blockchain with smart contracts, up to February 20th, so the Punjab National Bank fraud, so how blockchain can stop future Nirav Modis, right? Very, very interesting articles have been written on some of these topics. There are also many, many recent books on blockchains. So the book that I have liked most is this one by Don Tapscott and Alex Tapscott, Father and Son Duo. And it's a very nice, very friendly, informal introduction to blockchain technology. Those of you interested can take a look at this book. Then going back to this Bitcoin, the famous Bitcoin paper in 2008 of Satoshi Nakamoto, I think beyond Bitcoins, so there were several technologies that this particular paper talked about. Among all the technologies that this paper talked about, there are two fundamental contributions this paper made. One is to propose the blockchain data structure, and another is the notion of crypto economics, which is a confluence of cryptography and economics, in particular game theory, to come up with a peer-to-peer system which is absolutely robust. I think these are the two fundamental contributions that this particular paper made. Okay, so let's look at what the blockchain data structure is all about and what are the features of this particular data structure. It's a very simple, very powerful, with very powerful features. Okay, a blockchain network essentially is a peer-to-peer network. Now we are going to talk about different kinds of blockchains in this talk. There are what are called public blockchains, there are private blockchains, there are permission blockchains, there are consortium-based blockchains, and so on. So much of the initial discussion will focus on the so-called public blockchains. Now, in a public blockchain, you have a large number of users. Each user has a computing facility and also a data repository. And you can see that there is a ledger here. So this is the so-called distributed ledger, which is one of the fundamental building blocks of blockchains. Okay, so it's a network that includes all the transacting nodes. I'm talking about public blockchains here. Now, each user has computational resources and a data repository. Now, there are transactions of various kinds happening among the participants of the blockchain. So, transactions involving, each transaction will involve a subset of nodes. And groups of transactions are bundled into what are called as blocks. And these blocks are cryptographically secure. We'll see the meaning of this very soon. And then the blocks are included into the blockchain after miners do intensive cryptographic computations to produce proof of work. We'll get an idea of some of these things as we go along. Okay, so each block consists of a number of transactions. And in a given transaction, typically a subset of nodes could be involved. Now, each block itself is organized as what is called a Merkle tree. So here you have transaction 0, transaction 1, transaction 2, and transaction 3. So you can have hundreds of such transactions constituting a block. And you generate a hash from each one of these transactions, and hash 0 and hash 1. And from hash 0 and hash 1, typically SHA-256 is the hash function that is used in this technology. So you now combine hash 0 and hash 1 into hash 01, and then combine hash 01 and hash 23 into a root hash for that block. So if you are now given all these transactions tx0 to tx3 all the way to hundreds of these transactions, you can actually compute the root hash just by applying the hash function repeatedly. So if you want to verify that hash value, it's not going to be a difficult problem at all, right? Okay, now what makes the blockchain data structure very, very interesting is, now you have these blocks, and you have a number of such blocks which are chained together. And the chaining together of these blocks uses very intensive cryptographic computations. So this is what a blockchain will look like. So you have, for example, the Bitcoin blockchain consists of more than 200,000 blocks. And here we are showing block 51, block 52, block 53. And each one of these blocks is a Merkle tree. So you have all these transactions here. And out of all these transactions, you have a root hash that you have done. And now what blockchain, the way blocks are created and added to the blockchain happens in the following way. For example, let us say that you have created block 53. Now what is block 53? Block 53 may consist of some 200 transactions. And now every single user on this blockchain network now tries to create a block. And suppose a user has created a block with 200 transactions, and using these 200 transactions, this particular user now does what is called proof of work. Now this particular user creates a hash value out of it. But this hash value has to satisfy a certain condition. So typically the user will generate a random number, so it's called a nonce. And using the nonce will generate a hash value using SHA-256. And the hash value may not satisfy a criterion that is specified for you. For example, the criterion could be that the hash value that is generated should have 4 successive zeros in the beginning. If you want to generate such a hash value, then you will end up looking at a large number of nonces. So you will sequentially generate a huge number of nonces until such time you are able to generate a hash value which starts with 4 leading zeros. So that's the proof of work. And the Bitcoin blockchain adjusts the parameters of this proof of work in such a way that on an average it will take 10 minutes of time for a user with a powerful computing machine to be able to compute such a hash value. So now all the users will now create blocks. They now create these hash values which satisfy these criteria, and then such a block will then get added to the blockchain. So for example, block 52, assume that block 52 is added to this blockchain, but now you can see Of course, there is a pointer from, it's a linked list. So there is a pointer from block 51 to 52, from 52 to 53. Not only that, there is a pointer from block 53 to 52. And it turns out that the proof of work, so you can see the proof of work is the generation of that hash value, right? So you can see that every block has a proof of work, and every block is a Merkle tree. So the root hash that I talked about has nothing to do with this proof of work. And you can see that, so this previous block now, you can see the hash value that you have here is precisely the proof of work of the previous block. So what you're doing is the hash value corresponding to the previous block is actually stored in the current block also. So this makes it almost impossible for you to manipulate the blockchain that you have, right? Now, there are many more details here. Let me not get into all those details. But what we'll try to understand here is that we have created a data structure here which is almost impossible to calculate, especially if you have a very large number of blocks. You have here 200,000 blocks, right? Okay, so once a new block gets included, the updated blockchain becomes available at all the nodes. Now, this is a very important point. A blockchain is shared among all the nodes. It is synchronized because the same copy of the blockchain is available at all the nodes. It is immutable, not that it is impossible to completely replicate the entire blockchain, but the amount of effort that is involved in that is quite huge. So we can say it is immutable. It's a distributed ledger because it's available at all the user nodes, and it is created through a distributed consensus, right? Because all the users are trying to create a new block and get that new block included. And a new block essentially gets included after there is proof of work that is done by the user who has created that block. Sorry. Okay. And then you can verify the truth because you can always verify the hash values. And then this is basically tamper-proof record keeping. Essentially, it's like a glorified database where you are keeping the records in an extremely tamper-proof way. The protocol itself is decentralized, and a very important point is that it completely eliminates the need for intermediation. You don't need any trusted third party in which you are supposed to have trust in order for the transactions to take place. So this is one of the outstanding features of blockchain. So if you have a number of entities which want to collaborate, now it is not that these entities should know one another. So because you have a distributed ledger which is like common knowledge for all the players, then you can do business with anybody who is a part of this blockchain, and the trust is automatically generated because of the distributed consensus that has been achieved. Okay, the summary is that it is deep technology, uses cryptography, distributed consensus, data structures, database. It's not as sophisticated as the kind of databases that Jayant Haritsa works on. It's a very simple kind of a database structure, but cryptography is the one which makes all the difference, right? And that is the outstanding contribution of Satoshi Nakamoto. Okay, so these are some of the keywords that we should remember about blockchains. Distributed, it's naturally distributed. It is shared because that ledger or the distributed ledger is available at every single node. It's trustworthy. It cannot be changed. It's immutable. It is also secure. We are going to see that you can build in a wide variety of cryptographic protocols, which will provide different levels of security into the blockchains. There are no intermediaries. No intermediaries are necessary. It's highly democratic because almost anybody can become a part of the blockchain network. And another very important aspect is that it enables execution of the so-called smart contracts, about which we'll come to know very soon. Okay, so now let's. You have a question?
It's shown that picture that the hash is written in the previous block.
Yes.
So when is that written? At the time of creating, accepting this new block, when it's written by who?
So as soon as that hash value, as soon as the proof of work is generated, and then there is a previous block. There is a pointer now from the previous block to the current block. So it's exactly at that point of time that this proof of work gets stored in the previous block. So if somebody wants to tamper with the blockchain, if you are in a current block, now you have to somehow ensure that the proof of work for the current block is the same. Not only that, the proof of work for all the successor blocks are also the same, which is almost an impossible thing to do. Okay, some key topics. For those of you who are familiar with distributed computing and the Byzantine generals problem, the way the mining happens in blockchains, the way distributed consensus is achieved in blockchains is an outstanding way of solving the Byzantine generals problem. So one can show that there is a Byzantine generals problem here in the blockchain when blocks are getting added, right? Because there is a consensus that is involved here. Again, in the interest of time, I will not get into too many details about this. Second thing I want to say is that apart from the Bitcoin blockchain, there are two other blockchains which are now extremely popular. There are many other blockchains. One must mention the Ethereum blockchain, which is a contribution of Buchanan and Gavin Wood. Like all legendary figures, he is also a dropout from University of Waterloo, and he developed the Ethereum blockchain when he was exactly 19 years old. But Gavin Wood is a little better. He's a computer science PhD from the University of York. Then you have so Ethereum blockchain is actually a public blockchain. One of the nice contributions of the Ethereum blockchain was to introduce the notion of smart contracts. Then you have the Hyperledger project. It's an open source project. It's an open source technology for a standardized digital ledger. And companies like IBM and Cisco are playing a very important role in the Hyperledger project. And it's actually becoming increasingly popular. So at this point of time, for digital currency, the Bitcoin blockchain turns out to be the most popular. Whereas for business-related blockchain applications, Ethereum and Hyperledger are equally popular. And we are going to talk about permission blockchains, and they're also becoming increasingly popular in different domains. So permission blockchains, they are extremely valuable when the participants in the blockchain already know each other, they already have long-standing relationships, they trust one another, but they want to execute mutual transactions more efficiently and securely. So they would like to leverage upon the other advantages of blockchains. So in this case, for example, the identity of nodes adding blocks may be known, only certain nodes are authorized to add blocks. So here, the blocks are added only by a subset of selected nodes, and the overhead of proof of work is completely eliminated in permission blockchains. So permission blockchains are for very standard applications, for example, consortium of banks, or for supply chain partners, where the entities already know one another very well. So finally, this is another very important notion in blockchains. These are smart contracts. So my way of describing a smart contract is that it's a software program. It's actually a software agent which has a public key and a private key. That's all. That's a smart contract. Smart contract can do a wide variety of very interesting things. It's actually executable computer code. Self-executes when some conditions are satisfied. There are two examples here. One example is in insurance, smart contracts can pay out against insurance policies without policyholders having to claim, right? So this may be like a permission blockchain for insurance industry. A smart contract there will essentially take care of all the routine kind of transactions that will happen for insurance policies. Now, one of the emerging applications of permission blockchains is for academic transcripts of universities. There was a report recently that all the academic transcripts and also the grade sheets of all the students in all the IITs will now be on the blockchain. So if that happens, then a student, there's a smart contract there. For example, would be a student will get automatically selected for an interview based on transcripts on the blockchain. Or if a student is eligible for example, in IISc, when a student completes a comprehensive examination, the scholarship will increase from 25,000 to 28,000. Right? So you can actually write a smart contract which will ensure that from next month onwards, 28,000 will be deposited into the account of the student. Right? That's a smart contract which can do the job. But smart contracts actually can be very, very complex programs. They can do very complex things as well. Okay, so these are certain things about blockchains. Now let me get into some applications, right? Okay. So the land registry projects, which we talked about in the beginning, turns out that there are many startups working on this particular problem. And in countries like Honduras, Ghana, and Republic of Georgia, government actually has sponsored some of these projects, and all the land titles have been put up in a secure ledger to ensure that property owners feel secure and assured about that landed properties, right? And turns out that in the last 1 year that this is operational, looks like land record related fraud has been completely eliminated in these countries. It's actually a proof of concept, but this is a very good example where blockchains have really contributed to something for the society.
But I mean, here you can't deal with legacy, right? I mean, there's already fraudulent documents in there. If you record them,
right. So legacy will have to be handled carefully. So that will be a totally different kind of a project, right? So because the legacy records may not be very clean. So if you are starting afresh, right, which is what I think they did there, it makes good sense. Then, so R3 Dot is a fintech, is a startup in the financial sector. Turns out that 80 different banks have come together. And this is not, again, like a public blockchain. This is actually a consortium-based blockchain. So all the transactions that happen among these 80 financial institutions are all on the blockchain. So in this particular case, there is security of transactions, there is immutability of all the transactions, there is also efficiency in the way the transactions are completed. So you get all the other advantages that you can think of by having a consortium-based blockchain. So this particular platform is called Corda. And there is also another parallel effort in coming up with another consortium-based blockchain for financial applications, which also is. Then you have a very interesting startup called Hyperledger. It's a secure digital ledger for valuable assets. This has been used very successfully in the case of diamonds, for example, or jewels. Now, it turns out that more than 1.6 million diamonds are in this particular blockchain. So why is it useful? Since this is a distributed ledger, which is available to everybody who is interested in buying diamonds. So you can actually verify authenticity of all these assets and promote ethical trade. So basically, Hyperledger offers a digital ledger which tracks and protects valuable assets throughout their lifetime journey, right? From the time they are mined all the way up to the time they're consumed by somebody. Now, you can prove the provenance, the origins of this particular product, and also verify authenticity. Now, one thought that would immediately occur is why not use this for eliminating counterfeit drugs? Right? This is an application which will have enormous significance. So indeed, it turns out that there is actually a startup called Hyperledger, which is already looking at this, and these are the two pharma companies which are collaborating together. And so this basically, you are creating a blockchain tools for managing pharma supply chains. So here, the drug companies, the wholesalers, the distributors, hospitals, they record drug deliveries on the blockchain, and verification can be done at each step in the distribution process, right? Now, there are lots of issues right, involved in implementing such blockchains, right? But if it is done successfully, then it has the highest potential for eliminating counterfeit drugs. And you cannot imagine an application which is more societal or social good than this particular application, especially in the context, in the Indian context. Okay, I was also talking about tamper-proof academic transcripts. So this is something that can be tried out for educational institutes. Now, the use cases here would be you authenticate and control usage rights to educational data. It will reduce the headache of submitting test scores and transcripts. So if a particular university wants to verify the authenticity of the academic transcript, all that it has to do is to take whatever is given by the student and compute the hash value and ensure that that hash value is actually present in the blockchain, which actually is storing all the academic transcripts. And can enable smart scholarships, automatic admissions, and so these are a wide variety of use cases supported by this one. Then IoT-based services. So as you know, IoT-based services are now becoming very prominent in areas like healthcare, home automation, smart cities, supply chains, energy industry, and so on. What is the current status here? The current status here is smart devices are connected to the internet or cloud. So you may have millions of smart devices. You may have a very large number of smart devices. They are connected to the internet or sometimes to the cloud. Now, there are many services which are offered by many of these companies, and these are analytics based. Now, because you are looking at the cloud-based services here, it becomes rather centralized, and it is not scalable. If you have a very large number of IoT devices, then it doesn't scale. Security is a big question mark. Then there are no standards available here, and it could also turn out to be very expensive. Whereas, if you are not trying to use blockchains for this application, so how do the blockchains make a difference here? Blockchains will offer a distributed solution here. How? Now, devices could connect directly to distributed ledgers, right? So you know that this ledger, this digital ledger, is now available at each and every node. So it becomes a naturally decentralized problem. Fine. So scalability, scalability is ensured, and security is also ensured because you can build in cryptographic regulation protocols which will ensure security and privacy requirements. So this is one area where blockchains are being proposed. Okay, so having said this, in the last 6 months, what we have tried to do in the Game Theory Lab, I'll try to describe a blockchain-based platform that we have tried to build. Now, what is this platform? It's a trusted B2B collaborative market platform. Right? So it's a it has implications in the supply chain context. Assume that you have a bunch of enterprise buyers and enterprise sellers, right? You have buyers and sellers. Now, in a traditional supply chain setting, the buyers and sellers may be known to one another. But in a global scenario, the buyers may not know the sellers may not know the buyers. And yet, a blockchain-based platform can be used for such applications. So what could be the requirements here? The requirements could be the following. So buyers procure goods and services from the sellers. So the sellers are offering goods or products or services, assume. So the buyers are trying to procure those goods or services. Now what we want to do is, we would like the sellers to provide high quality goods. Assume that the sellers can provide either high quality or low quality. Now what we want to do is, we would like the sellers to provide only high quality goods, suppose. Then we would like the buyers to provide honest feedback. Now the buyers are the ones who will provide feedback about the quality of the goods. So the buyers actually get the goods or the services, and they will know the quality, and they provide feedback, right? They provide feedback. We would like all the buyers to provide honest feedback. Now, a very important requirement is business sensitive information not to be revealed, right? So many of these companies, will have business intelligence or some information that is sensitive. So we have to ensure that this sensitive information is kept private to only those players, right? So you are now trying to talk about a global B2B platform where you have buyers and sellers who may not know one another. And then we would like the sellers to offer only high quality goods. We would like the buyers to give honest feedback about the products or services that they have received. And we would like information access to be highly selective, right? So we would like to achieve all these objectives, right? Now, a public blockchain will not help us in this, right? In a public blockchain, in some sense, every node has access to all the information, right? So it has to be a blockchain which is not public. It could be a permission blockchain, or it could be a consortium-based blockchain, or any other structure that you may like to come up with, right? Okay, so let's try to slightly formalize it, right? Suppose n is the set of participants in this blockchain, right? So our objective is to be able to build such a platform. See, one can say, why not build an internet-based platform with a nice database system and so on? One can do that, but the kind of requirements that we have stated may not be possible to be satisfied by such a platform, right? There are certain requirements about the behavior of the buyers or sellers also here. So this is where we were trying to leverage some aspects of mechanism design. So let's suppose you are able to design a mechanism which will make the sellers and the buyers to behave honestly. Suppose you have a mechanism. What we want to do is, we want to now come up with a blockchain-based implementation of that mechanism, which will extract honest behavior from the buyers and the sellers here. So a bit of notation here, if you have N as the set of participants and E as the set of all events or transactions that are happening, if little e is any typical event or transaction, NE is the set of participants in the event E, and RE is the record associated with the event E. So these are important, right? D of H comma RE will give you the subset of data fields of RE accessible to H. So H is a node, and RE is the record or the data associated with the event E. But you may not like to reveal the entire record RE to H. So this will give us the subset of data fields of RE accessible to H. So D of H is any typical node, any typical user here. So D of H is overall data accessible to H over all the events, right, which are happening in the blockchain. And D of U could be the entire universe of data accessible to all agents. In other words, DU will tell you all the data that is accessible to all the agents, but there is so much other data that may not be accessible to the agents. So in order to set up the mechanism design problem here, what we did was to define a social choice function which can be computed by an oracle having access to the data D of U, right? Now, let me skip some details here. And I will only show this. So we want to now come up with a blockchain protocol P, which will simulate the social choice function F, such that given node H, which does not belong to NE, NE is the set of nodes which participate in the event E. If H does not belong to NE, it should not be able to infer NE. So I was talking about business sensitive information. And then it should also happen that no node H can infer any data of DU minus DH. DH is all the data that is available to node H. DU is the universe of data. So you can see DU minus DH is the rest of the data. So this rest of the data should not be accessible to the node H. So if you have such requirements, so it turns out that you have a mechanism which will make that happen. But what we want to do is, we want to now implement such a mechanism using a blockchain-based system. So what we essentially did, right, is that a solution to this problem in the blockchain context will be that you can actually use a permission blockchain with smart contracts, right, where the smart contract is essentially a programmatic representation of the mechanism that you have designed, right? Maybe the mechanism that you have designed, an incentive compatible mechanism which makes the participants to behave honestly, could be broken down into several smart contracts, right? So all these smart contracts now are part of the blockchain. And as I said, smart contracts could be designed using game theory. Privacy of business sensitive information could be ensured through carefully designed cryptographic regulation protocols. And such a blockchain based system is satisfying all the requirements that we started off with. And as I said, the buyers and sellers may not know one another, and buyers and sellers will find it trustworthy and participate because of all the properties that blockchain technology offers, right? Okay, that's just a glimpse of what we have tried to do. But in general, you can take any mechanism and then implement it using a blockchain. For example, if you want to have a trusted VCG market, which uses a Vickrey Clark Rose mechanisms, so here is a very simple way of coming up with a blockchain-based system which will precisely implement that mechanism. So since it's already 2:45, I will now skip this portion.
Compute the function D that you showed.
Pardon?
That function D which controls what information are available to which node. Where is that function computed?
Which function?
D.
Oh, okay. So this is a permission blockchain. So in a permission blockchain, essentially there is a subset of nodes which are called as monitors, right? Who will be entrusted with the job of computing such functions, right? In a public blockchain, right, that situation will not arise. Okay, I just wanted to say that here's a summary of what game theory has to offer to blockchains. If you try to model them using non-cooperative game models, it turns out that either Nash equilibria do not exist or they're trivial. If you try to use cooperative game models, the solution concept, the core is empty, so all coalitions, all mining coalitions are unstable. And then it turns out that most of the reward sharing protocols among players who do the mining, these are not incentive compatible. So it's actually, if you try to look at, if you try to apply game theory to study the dynamics of blockchains, most of the news is bad news. So the summary is blockchains are cryptographically strong but game theoretically very fragile, and the belief is that if you can use mechanism design, blockchains will become more and more robust. Okay, so let me skip this slide also, and come to the conclusions, right? I'll take just 5 more minutes. So the reality check is the following. Question, is the blockchain technology ready for immediate deployment? Immediate answer is definitely not. And I have not seen a single blockchain system completely implemented and completely deployed and working in a flawless manner. At this point of time, only POCs. So we talked about a large number of startups, but all of them are only proofs of concept. If you're looking at public blockchains, the energy consumed is absolutely unsustainable. For example, the energy that is consumed by all the mining that happens in the Bitcoin blockchains is more than 100 times the energy that the company Google uses, right? It's actually 100 times that of Google. Limited scalability, again, public blockchains, they don't scale well. Throughput is low, and they're also very slow. Now, no signs of formal verification of smart contracts. So they have designed several programming languages. So one language is called Solidity. This is in the Ethereum context, but a lot needs to be done in formally verifying some of these smart contracts. And the way incentive design is done can be improved quite a lot. There are no standards, and this is a standard item that everybody puts these days, threat of quantum computing. That's the reality check, right? So this scenario is not very good. What's the promise and prospects? Very clear that blockchains enable, at least in some chosen applications, secure, fast, immutable, trustworthy, and transparent solutions, right? Improve existing applications and help launch radically new applications. We have actually seen some examples of applications where blockchains can be used. And then they can support effective healthcare and welfare programs. That's why I put industrial and societal in the title of the talk. Hopefully clean up unethical behavior in high value businesses, right? The bottom line is that technologically it's a very strong technology, very deep technology, right? Anything may happen to all these applications and so on, but the technology itself will survive. Some of the technical strengths which make the foundation for blockchains are so strong that the technology itself will survive. Okay. Again, low-hanging fruits are there. They will get implemented in the coming years. So the hype will continue to be there. And this room will see more and more audience when blockchain talks are given. But real transformation, I think, will have to wait. So my summary is that blockchain technology is like TCP/IP. Right? TCP/IP was developed in 1972, and then not many people cared for it. It was waiting for a very compelling use case. I think email was an extremely compelling use case for TCP/IP. It just took off. And then in the mid-90s, when the World Wide Web came, I think there was no stopping TCP/IP. So though it happened in the mid-90s, I think it has taken another 20 years for the full power, the full potential of TCP/IP to be realized. I would say that blockchain technology is also like TCP/IP. It may not take 30 to 40 years. It will definitely take 10 to 15 years for the full power of TCP/IP to be realized. There are some very nice sources where you can read up about blockchains. So this book by the two Tapscotts is an excellent one. And the RBI white paper is also very well written. So those of you who are interested in financial applications in the financial domain must go through this. This is a must read, Satoshi Nakamoto's paper. As I said, it's only an 8.5-page paper. It will not take you more than 1 hour to read. If you have not already read the paper, please read the paper. So this paper by Buterin about Ethereum and also Gavin Wood about Ethereum, these are also extremely well written papers. Then Communications or the ACM published a very nice paper, Blockchain Beyond Bitcoin. Then there are many other reports here. I would like to particularly mention the special issue of IEEE Spectrum, special issue on blockchains. In fact, much of today's talk was put together by reading the papers from IEEE Spectrum 2017. And if you're one of those interested in trusted B2B platforms and the work that is going on in Game Theory Lab, please do read this paper. It is not accepted in any conference so far. It has already been rejected by a conference. So we have resubmitted it to a conference. Hopefully it will get accepted very soon. So with this, thank you very much. Thank you.
Since I gave a seminar here, of course it was in P303. Second, last 15 months I've given about 20 talks on this stuff. But I must confess and feel heartened that we have such a distinguished IIIE CS intelligentsia in one hall, and it's a great feeling. Never had this before. IISc always has had great audience. Once upon a time, like me, sitting like here, like this, for something seems new and seems a kind of a mystique or mystery associated with that. So 45 minutes, let me try to dispel some of those. There will be some technique, some technology, some science, some math, and I, at my age, try to get more involved with issues which are societal, in a broad sense, but more sociological, more economics, or where other aspects of human endeavor and intellect are challenged. So this cryptocurrencies is like that. This was described. Now a word of disclaimer. In a talk in Dhruva Ambani Institute, my professor friend host, even before the talk said, this place, the first question you will get is which coin I should invest in. Now, exactly after the talk, the first question was that. So I said, I'm not an investment banker, but today, now I modify the answer. If you want to know where to put your money on, there is a nice startup, again, in the spirit of what Narahari flashed. One Rishikesh, he has started a company which is incubated at IIIT. He is a student of Professor Hansda, and I'm working with him on this company's thing. It's called Zero Labs. Put your money on that. We want to get our coin out. Okay, so now some, and of course, the last whimsical part to say, about a year and a half ago, it was just 2 slides. Now it is about 60. It is almost like the Bitcoin stock going up. I want to bring it down these days. So from $0 to $17,000 to $11,000, it's something like a market value of a Bitcoin. So my slides are also going up and down. It's been going up. Actually, the Bitcoin phenomenon, as I think, earned disrepute to this crypto and currency. Actually, it is sound crypto. It is sound currency from financial and fiscal points of view. But as the mystique is being spread around, it's only a bad name for both. That's why people are wondering, either in governance or in law or in science, what is this animal? Whether we should be living with it or will it be there? And as Narahari put it, maybe next 10, 15 years will tell. Whether the cryptocurrency as touted by the Bitcoin, Ethereum, Litecoin, and a few others of this same genre, whether they will be role models, they will survive, or some alternative forms. And here is where, like academia, we have an announcement for one of our own, which was a project again done like several years ago and a few times in the last 20 years. It's also called digital cash, and this is known to cryptography about 25 years ago. I'll talk about that. It's actually it's a precursor to this much built cryptocurrency. Okay, that's more a cryptocurrency, and just so that we'll say what all these things mean. Where are the arrows here? Okay, so once again, there are several things here, and 45 minutes, as I said, we'll skip. We keep accumulating the slides, but morning I had a talk at a forum organized by Department of Telecom to some local intelligentsia in a hotel, and so I skipped some. Here we will skip some. But again, Narahari has already set the nice tone for the nice interplay of this notion of cryptocurrency and blockchains, which is something which will last for some time until all the hypes get toned down and reality sinks in both the blockchain apps as well as the money apps. So definitions have been set, all these properties. Now I will be spending more time on cash, money, currency, and I'll probably, hopefully if you have time, defend a few questions. All these are precursors to today's cryptocurrency, as you've known. All the references, names, works are all there. But to put it short, something like this is a case I'm going to make. This wallet we carry, there's a physical cash, money. Money comes in many forms as instruments, as what's called fiat money, which is a state-supported currency, is called fiat currency. Fiat means so be it. Cryptocurrency is not so be it. Cryptocurrency is just made by us. Okay, so and its instrument forms used to come in from classical ancient times to modern times. Finally, printed paper, coin money is called. Then plastic money, cards, all kinds of cards. Then advice money, paper money again, checks and advices and so on. Then bit money, just send advices by bits. And this money which is physical, that is the coins and money, which we carry today. All of this coexist. There is a place for fiat currency in the form of physical money, paper, coins, which we carry in our wallet. And once again, there's a lot of societal differences and so on. I'm going to spend a little time on that thing because cryptography, economics, finance, they get bundled up with these new animals which evolved in the last couple of decades. So eCash was something which is quite early in the era of cryptography, 82, David Shom. It's a digital form of the physical cash which we carry. Cash is, after all, now the physical form is a token, and it has many definitional notions. It's called a store of value, medium of exchange. It's fungible, it is exchangeable, it's universally within the jurisdictions valid, it's ease of use, it's private, all these properties. That's the thing about this physical form of the cash. A digital form of that cash called eCash seemed to be a nice thing to have. And this was touted early on in the day of cryptography. Similar principles were there in Hashcash, and as the name implied, and as a fundamental pillar of the data structure called blockchain, which the crypto infused into that, is this notion of chaining successive quantities of data in the form of blocks into compact, incontrovertible, with a compact, incontrovertible digest, which is small added. So a big thing, many bits to a small thing, which is a many to small mapping, which is usually called a hash or a digest, which is incontrovertible in the sense that the inverting is computationally hard. So it's these are typically used in cryptography, one-way functions, cryptographic one-way functions, which are easy to compute one way, forward way, F mapping a message across the key space to a cipher space. That is easy to compute, polynomial time computable, the length of the inputs, but not known to be polynomial time invertible, F inverse of Y, which is one argument in the range space, to get either of the two arguments in the domain space is probably, it's not probably not polynomial time, but not known to be probably to be not polynomial time. So essentially like NP hard, not quite NP hard, but kind of a hard situation. So such functions are called cryptographic one-way functions, and hash functions typically used in cryptography have that nature, and so they have this propensity to be chained along data structure of blocks or data types or whatever, in a manner such that verification of any part of the chain from any other part of the chain is quick, like the Merkle trees and so on. But inverting, which is meaning your fudge something in the input argument so that you get the same hash value, is purportedly not polynomial time. So this behavior helps us to do hashes in successive chains, and this gives to blockchain. Now, hash chains were used in eCash and Hashcash and some other different forms of cryptographic hash values like Primecoin and all that, evolved to the cryptocurrency, so Nakamoto, the mystical figure, the idea is to make a system out of this hash cash kind of philosophy, which will make all those nice properties which are desirable for computing. The distributed consensus, ledger, transparent verification, all those kinds of things. So they evolve like that. They internally use constituents which are based on digital signatures and so on. And these all lend themselves to some exciting new prospects in cryptography and applied cryptocurrency research. Okay, so now that's one side. But now our final end goal I will show is a project which I've been doing here some time ago, and then want to reactivate with that Zyro lab, is to make our own coin, which are not quite Bitcoin-like, but crypto. Fine. So there is thing about acceptance of some new phenomenon. So the cryptocurrency phenomena, in particular the realizations of Bitcoin, Ethereum, all of us suffer from, as a financial entity, suffer from this completely ununderstood and little mystical things about value, its role in transactions, its privacy versus security, all these concerns. So these are the concerns which are actually, plus the acceptance when you accept money. After all, money itself evolved from very nebulous thing like gold. In fact, there's a lot of analogy to the gold mining, gold digging, making money out of gold, which is called minting, and the terms which is used in crypto are reminiscent of that era when there are completely, the first people take all, whatever is there, and the later people find it difficult. And at some point, you have to have in order anarchy not to set in, evolve some standards about valuation and so on. So gold values were standardized, then of course the dollar got standardized, and the rest of the world and all that. So this kind of thing also is creating a problem. So these are less understood. But I want to dispel the difficulty with all these things. There is again a place for physical cash. So this is the small case I will make for 5 minutes, because this concerned me a lot in the last 2 years since demonetization. Now, this the tenor of the talk is nothing to do with the political incorrectness about or correctness about demonetization, but about the importance of what's called physical cash, money in the form of physical tokens, which will continue to prevail in almost all economies. And there are lots of stats and things like that. The last line is just more or less important. The rest of it you can ignore. Currency to GDP, we have about 10.6. All the numbers which I show in the next few slides, which I continue to collect from the RBI sites and so on, reflect that. About 16 trillion rupees, 10.6% of the 10 or 11. Now it's about 150 trillion rupees. So it's about 10, China 9, US, UK 8 to 4. So varies. And something to say about the last two add up 140 billion. See, forget about all the coins, lower denomination. About 140 billion coins accounting for 12 trillion rupees. 12 trillion rupees then was about 12% or something like that, let's say. 2013, then 16, when all this fun happened, 15.8 trillion in the high denomination, 500,000 value, which is about 24 billion instruments were withdrawn. And remarkable that this country survived while Venezuela crashed around the same time, but this kind of thing. And anyway, most of all of it came back, which I predicted in November 16 itself. And so this is about 17, and I put it behind. Oh, what happened? 12. So 15.5 return in July last, and then off the 15.8. So this I predicted as a joke that it's a total embarrassment for anybody who attempted this kind of action. Now one recovered by what's called as remonetization, which is bringing almost to the same level, except that little less it has come down. Instead of 16 trillion, it has come to 13 trillion money in circulation, as it's called notes in circulation, and some numbers values, it's increased. This is June, that is March. So it's actually leveling off at the same thing. All it means is a propensity and the natural inclination of our country people to be wanting to use this. And it has also nothing to do with just a emotional attachment to this or something. It's actually more economic, more pragmatic as to the role of this money in transactional economy. All of you might have known in many of the sociological phenomena, there is this thing called power law, which operates, and which is also called a long-tail distribution, which is just that. So for money, for example, you put on the y-axis value of transactions, and on the x-axis, the number of transactions of that value. Okay? So what it means is, there will be per day, very few transactions of 10 crores. Okay? One transaction of 10 crores. Value 10 crores, 5. 1 crore, this. 10 crores, this. 1 crore, 10 lakhs, 5 lakhs. And then all of us, cafeteria, 10 bucks. I hardly spend any money over, but most of us spend 20 rupees, 30 rupees, 40, 2 coffees, 3 coffees, whatever. So this number of auto rickshaw fare, taxi fare even, large number of small value transactions, asymptotically going to a tail which is very long, and then a small number of large value transactions, and the area under this curve adds up to the GDP. So it's all possible to model and all that, but the point is number of transactions which account for the value is in terms of this instrument called, this lowly instrument called physical cash. That's it. That is a different thing. Why it should change, why it should remain like that, no question about it. As long as the economy is about that, it will remain. Okay, this is one side. And this is so in most economies where such events happen. Where it did not happen, like what we meant was digital. The countries which Narahari said, we also mentioned the reason. You leapfrog. You never had cash. You never had transactions. So electronics, digital networks were there first. So they leapfrogged into the digital money like the M-Pesa and things like that. Okay. Having said all this, I will make a case for this in our constant research endeavor to emulate this digital e-cash. And somehow, which we did, was to make a project in which you have mobile phones with something analog of this physical wallet, which I call the mobile wallet. In two mobile phones, you have mobile wallet with this digital avatars or digital make-believe of the same denominational notes, because that's what you're used to. In fact, the new project we did, we put the note pictures also. So like in your wallet, 500, 10, 100, like that, the same number in your, just click. Then the thing was to be able to transfer. In a peer-to-peer transaction economy, you just take out the money and give it to you. And that's what happens in this long tail of the transactional economy of the country, like in a place like Yashwantpur market or something. I'm always fascinated by the amount of money which rolls. Not big money, tens, hundreds, thousands, a lakh, which rolls between small time vendors to the sabji wala, to the auto rickshaw wala, to the big truck wala. It goes on. Okay, now similar thing can be done. That's what we do in the department, a mobile phone, and then transfer money by clicking to the other phone, and the interface could be any quick interface without Wi-Fi or whatever, but even NFC or we did it with a QR code and NFC. Now, what is the crypto? So when I transfer this money to this money, one of the fundamental problems with crypto money in the eCash version, as opposed to this money, is that I can give you this money, but I can make a copy of this and give money to the same thing. So that's the idea. A Xerox copy of the same money can I spend. It's called, in the crypto world, in the eCash world, this syndrome is called double spending syndrome. And digital world, it's so easy to copy. So these are all digital bits and numbers, and then you can make multiple copies of them. So you make a copy and then circulate. So this is called double spending. We know the obvious answer that, well, this can be done in this physical money also. I can make 100 10 rupee note copies by Xeroxing. It won't fly. So why it won't fly, always we forget. Now, in the crypto world, in order for it to not to be done, there are some very devious little tricks of crypto which are employed in research literature long ago, which are called double spending detection, double spending prevention. Now, it is amusing that you can make a digital copy, but the digital copy should be somewhat different. Some aspects of, you've got watermarking, these are called, there are research, different ways of doing it, and also such double spending detection prevention, there are some devious cryptographic means by which you could do it, but they are expensive. In fact, one of our earlier papers was in that by an ME student here. With all that, the idea was to build a system in which we can handle physical cash with the same fluency, ease of use as a electronic cash. So the double spending is a problem that requires some kind of a mediation, an intervention by a small trusted third party. See, almost all of crypto, at the back, there is some trusted third party. Somebody has to be trusted. It could be one in a tree or many in the subtrees and so on. With the invocation of a trusted third party or what we call a centralized coin issuing authority, verification authority, all that kind of thing, it can be managed. And in early days of eCash, companies were started like this, but they folded because this other medium wasn't there. This internet or mobile telephony, nothing was there. But now with the coming of the mobile and other things, the ease of those things are the transactional ease between peer-to-peer, the instruments are there, so it's time to facilitate that. So that's the import of this. Now, there's a, okay, so I have more slides to show this in other countries as well and so on. So, now some other things which I don't have to now fortunately go through, but the proof of work is costly. There is one thing which is happening in the world. Permission blockchains is one way to obviate lots of proofs of work, but still some proof of work is required somewhere. Another way is to what we call in the crypto lighter proofs of work. Now, lighter means security is not compromised, but the resources used to get that is quick. There's again a conflicting requirement. So this one way to do would be to compromise, not compromise, use some what you call, this is more practical. For different levels of requirements of applications, you give different proofs. Like you spend money in coffee club, they won't give any proof. After all, if you double spend, as we said, this our case, or wrongly spend, you will catch you next day. So it's like there are many things about cash, which the trust, and in fact, blockchains has introduced new words also, again, along with the hype. It's called it's called the new age trust. So people would tend to believe blockchain is a trust thing, no matter who implements. So likewise, trust is usually associated with a community in which there is some implicit trust. And that's what's happened in what's called as local economies, small economies, big economies, and so on. So I just said coffee club for it. In fact, coffee club, somebody said they used to print coupons, and then they stopped making coupons because somebody forged coupons. And the point was, if somebody forges a 10 rupee coupon, he comes twice, the third day he's caught. He's rejected by the system. So generally, these digital cash systems, when it was touted in financial cryptography, was that they are used for small value payments, large number of small value payments in a community-based payments. So once I was telling Professor Narahari that it's a time we have an IISc money. You know, you have IISc tokens. Money is nothing but tokens, coins, coupons, and this is what makes this money little more appealing. That is, this cryptocurrency in general, eCash in particular, appealing because they have all these properties and they can be fluidly, seamlessly used in a digital local community. So we had our architectural proposal saying IISc coins, and then now you still need coins. Coins are tokens, like Xerox tokens, coffee tokens, health club medicine tokens, or whatever. Okay, and you change tokens also. You extend this logic, IISc tokens to pan-IISc IIT tokens, or and so on. And all this is digital. There will be currency conversions, exchanges, all this is digital. It's all possible. So The point was, in a local economy, you can do with local instruments. And this is what makes, I'll tell you, extension of this reading is that in a recent budget time, a natural question in Parliament about this cryptocurrency was to Arun Jaitley, what is it? What is this cryptocurrency? What is Bitcoin? So, very carefully worded. I think now they have learned a little bit after all this fiascos of last year. Cryptocurrencies are not illegal. Now, you have judged. What does it mean? And this is a finance minister's statement, which is true. Like, for example, Sodexo coupons, which is given in many of the companies to employees, are not illegal. Okay? So, the blue tokens, the green tokens are something of IISc money. It's not illegal at all. So, all of us can draw 1,000 tokens from the finance office and then use it freely. Now, I'm just saying the digital analog of that. All of this is digitally signed and above board. And all other things are also very clean in terms of taxation, in terms of counting. Everything is possible. So, in some sense, in a digital economy, there will be a place for everything. And there is one bigger reason for also not going for other type of money instruments like cards, like credit cards, debit cards. Credit cards are bogus because there is so much overhead on credit cards. Merchant discount rates are very high. So there is always this debate and dispute who should be where the burden should be placed on. So with the result, acceptance of cards is going to be tough. On the other hand, anyway, I'm now talking about the entire spectrum of payment systems. Somebody will say I use cards, somebody will say I use cash. That's not the issue. I've already given lots of stats about what is a transactional economy. So everything will have a place. Then there is this place for minimizing the overheads, minimizing the cost of running systems, and minimizing the cost of the burden on the wherever the consumer should be least burden, and then wherever it's to be passed on, it's to be passed on. So with all these things, cash is still king. Now that's a nice cliche. It's used in the research papers also. Okay, now this one part. Now a little bit about, I think, cryptocurrencies will start. The history of this, David Shom, Brands Cash, there is a company of his student, the Millicent, Beck had a Millicent, and many other things. And then we had some papers, and of course, recently we touted it again. We put some virtual money, we call it VM coins, and then some hash chains and things like that. Also, the IISc chains were based on some hash chains, which are based on some cryptographic hash function designed by one of our students here, Srikanth, in his PhD. And then we got a patent out of it. And now using all this thing, we want to make some systems. All this also will lead to something called using lighter alternative proofs of work. So Bitcoin, like the one thing about Bitcoin and mining, the analogy to digging. So this I will illustrate by numbers. Digging gold was easy initially. Everybody went to Kolar or everybody went to the Wild West then in the US. So there was a lot of gold. So the early movers picked on a lot of gold. The later fellas had to struggle. Then at some time everything gold is gone. But the only thing is the total value of gold, total amount of gold remain constant. Bitcoin or cryptocurrency has this first part which is similar. You can mine only that much. So it's called the digital gold. In fact, the Arabs used to want to call it petro gold, but they mistook it. But petro gold is gone. Real gold is that much. Whatever was there originally is there, because gold does not, vanish. So it has to be something immutable. It has to be a constant store of value. It has to be only this much. I mean, from here, this much, inflation proof. You can't make more than that. You can't make more money. You can't make more money unless you produce. You can't print more money. If you print more money, it's wrong economics. So the gold digging analogy to that is correct, meaning it is easy to get in the beginning. It gets harder and harder to get. There is a saturation. How do you achieve it in cryptographic things, computational things? So Merkle trees and all that you already discussed. I'll just show this quickly. Now this one says Narahari mentioned the figures, it's almost right. 12.5 bitcoins per block. Blocks are fixed at 1K or something, some number of bytes. It's just standard 1 kilobytes or something. But the interesting thing is, total number of bitcoins is capped at 21 million and expected to mine all 21 million by year 2140. Actually, some of these little things in books or technical literature always puzzles me and I try to work it out. How can you tell in 2140 there will be exactly 21 million coins you will produce by this process, which I'll illustrate. And that is the beauty of little math and some computing. Okay, so it all started at, let's say, 128 years before 2140, which is 2012. Actually, it was 2009. There is a way to estimate that. So obviously, it's based on computing power. Today's computing power, we estimate something, and then at today's computing power, it's about 12.5 bitcoins per block. Of course, the valuation part is all the gimmickry of the finance world, which is the least understood. It's so expensive, I think it may not sustain. It's total worth of, at least some time ago, it's about $250 billion, which is bigger than GDP of many countries. Okay, now the way to mine or mint a coin is set according to a crypto hash with a specified value. The leading 4 is set, but actually it is 72. So you can see there, given the hash function h, which is SH256, hx equal to y, x is the starting point, the one of those hex numbers here written in the block, and you want to get a y, that's given. The hash value of the input is there, output is there. X is there, y is there. Then it says the new block generation. At that point, we will say find a nonce, and a simple additive nonce. You keep on adding 1, 2, 3, 4, 5, 10, 100,000 to X, such that it becomes Z, where Z is of a special form. The leading 72 bits are 0, the remaining 184 bits are don't care. Okay. Now, the obvious thing is that there are 2 to the power of 184 such strings. All possibilities there. Out of the 2 to the power of 256, so the probability is 2 to the minus 72. So you have to do 2 to the 72 times. So 2 to the 72 times, you have to add n. Around n equal to 2 to the 72, you would expect it to get that hash value. That's all. Now today, this is the 72-bit 0 is the set thing. Actually, it doesn't matter whether it's 0 or it can be 1, 1, 1, 1, anything. Okay. To get any one, probability is 2 to the minus 72 for fixed 72 bits. So, but what does it mean? It translates to some exorbitant computing, which can also be calculated based on, say, current status, October 2000. Hash rate with the machines they have is 2 to the 63, which is phenomenal. Because I estimated the last line, which is our IISc Sahasrat, a petaflop machine. Every 10 minutes, you get one coin, which is 600 seconds. In 600 seconds, you get one coin. To mine that in 600 seconds at this hash rate, you require 2 to the 59 cycles, and whereas this is only about 2 to the 50 cycles. So about 59 hashes are 2 to the 63 hashes per second. So 63, about 16. You need about 8 petaflop machines at this rate. It's a very easy. Indeed, the hashing mining rigs in the Chinese consortia somewhere, the pictures are really mind-boggling. They probably use 8 to 10 petaflop machines today. And tomorrow, when the level is set to one more bit, it will be 2 times that. So that's the exponentiality taking over. So this you can craft. So after, suppose you make a big new machine, 5 years down the line, you can set that to 4 bits at a time. So you can keep on maintaining that pace so that you can say 2140, I will reach the 21 million coins. So this is something like a nice science engineering behind cryptocurrency mining. A little word about this mining. Again, the hype sometimes is funny. It makes money, it kills people, everything. So now, on the one hand, it has generated huge business for semiconductor industries. In fact, the 8 or 16 petaflop machines which is used by these mining rigs, the chips are made somewhere in the other parts of the these eastern cohorts of China. But more interestingly, now the Russian communities, the erstwhile Soviet Union communities in Latvia, they announced last week that, well, you want to mine coins, please come here. Okay, we will give you land, we will give you sheds. It seems they are well endowed with electrical power and then a lot of cold water. And so they say you can put mining farms and then mine. So it all sounds like almost like a mining farm in digging. No, huge computers running absolutely quietly, but with a lot of water cooling and things like that, and you pay taxes to them and they give you free electricity and they share the rewards and so on. So there is one other angle about a kind of a disillusionment about the cryptocurrency, in particular the Bitcoin genre, that it's not now anymore a level playing, in the sense that you and I cannot mine. And many people unwittingly go and buy Bitcoins. Okay, I wish they should engage in mining and beat the other people by new, faster ways of doing things and whatever. But in any case, nevertheless, there's no way anybody can mine except those people, find the new coins. These coins are not used for interesting transactions. Now, this is one thing about money part. If money, anybody can make money, but if the money is not used, it's useless. It doesn't gain currency. In fact, the word currency itself in the language, it means that there is something about that instrument which is very, very useful. It's current. Okay. So you make money and it's not used, which is what Venezuela did before it crashed miserably. There is no point in this country building even 2,000 rupee note is a fiasco. Even I find it hard to use 2,000. I mean, at our levels of richness. What do you use 2,000 for in India? Suppose imagine that you print a 1 lakh rupee note, which will happen in a hyperinflated country. So we must hand it to this great country that with many things which are wrong, some things are good. Somebody said we are on very stable foundations. The economy doesn't crash whatever happens. Notwithstanding demonetization, nothing happened. After demonetization, we remonetization and we forgot about it. What will happen is that this thing will have a natural death or a forced death because of these many futures. And the disillusionment from the cryptocurrency community is just the openness, the transparency, the distributed ledgers will be great. In fact, those are sound principles. Crypto is sound, economics is sound. In fact, the distributed ledger, I was drawing an analogy in the morning to other kind of banking audience. Imagine all our passbooks, your passbook, my passbook, all banks, all things. What is a ledger entry is in the accounting world, it is called the double entry bookkeeping entry. Okay, debt from where to whom, and then credit, debit, total. That's all. And absolutely simple accounting, and they gave a nice name for it called double entry bookkeeping. So I went and found out what is the double entry. Only these two entries are double entry. So get arithmetic. Imagine but hundreds of them, thousands of them, mine yours all in some database. Okay, just keeps on adding. All we have to do is to take one hash, take the hash of that, concatenate to the next hash, do hundreds of them, hash, millions of them, hash, put them into some Merkle tree. That's it. Anybody can verify. You can conceal your name, my name for privacy reasons and so on. So the whole history of all transactions is available. In the blockchain world, in the cryptocurrency arena, they are available in all the networked systems. So nothing wrong. In principle, nothing wrong. How does it matter? Your passbook and my passbook are visible, except it doesn't know your income and my name will type to our names. And so the Bitcoin did this by masking identities using some crypto masks and digital signatures and all that. And, all those are fraught with little problems of unhappiness, in the sense that it's not all that there's a way to bind the logs of the Bitcoin transaction ledgers and somehow figure out the name of the master identity and so on and so forth. So it's not necessarily truly private. It's not necessarily egalitarian in the sense that anybody can mine. So, and its rate is decided by some guys who got it first. and then there is a lot of market hype about its price going up. And the last of all, there are no transactional identity for small transactions. Got it? I'm also surprised, it's small figures I read here and there. I was looking at where all it is used, let's call it credible institutions. So, for example, okay, I was going to ask a very dangerous question. I was going to ask whether IITs will accept fees by bitcoins. Actually, there's nothing wrong, because finance minister said it's not illegal. Okay, what's the problem? I have Bitcoin and then I pay my PhD thesis fee or something like that. We should accept in principle. And there's only one university or one UK, Cyprus, they all accept Bitcoins for everything, but they also have some dubious identities. I think there is this problem, but as a financial instrument, it's quite okay. But the point is, the small value payments, the large number of small value transactions, all this, it will find it difficult to handle. Because if you have billions of transactions and they go into millions of blocks and so on, and then you have to get hundreds of such proofs of work of that nature, I mean, it's gone. So, and also, because every transactional element is what is hashed and chained in the Bitcoin block. And that's where I think President Narahari mentioned something about the evolution in practical world about permission blockchains and things like that. Now, these are not fiduciary applications. These are going to be real world applications on what you may call informational world. You know, like our mark sheets. Mark sheets don't carry any money. Mark sheets, land records, everything. The money is separate. So these kinds of information, digital information, nicely cry out for chaining by bitcoins or blockchains. The nature of the proofs of work and so on are going to be different. So I'll just spend 5 minutes on some other aspects of cryptography which are coming into the rescue of such things. But they're all again, emerging, and so all this very expensive integrity proofs. That's it. Rest of it. All these things are gone. Anyone can join. Verify data is okay. But anyone cannot join in minting a coin. So there are newer forms of proofs which are not based on just work. See, this Bitcoin thing is based on proof of work and very hard, boring work of digging, dig. And precisely you have to dig 2 to the 72 cycles until get the next one. So whoever has 2 power 72 cycles will get it, wherever you start from. And of course, they have a nice distributed consensus. Many people can get. In fact, that's how it happened in the beginning. People thought that everybody could join the mining race. All I have to do is say if it is 2 to the 30, I can do a short program for any hash function and immediately run it for an hour, get it. So can you, so can anybody. But if you have 2 machines of this, you will do it in half the time. But if you have 100 machines, you will do it 100th the time. If the difficulty level was 30 bits. It started like that. But the 30 bits machines all of us had, so we could, 2 to the 30 hertz machines all of us had. At some point, the degree of difficulty has increased, so the ability to do mining has come down to the big consortium. So it's no longer egalitarian. So the proofs are different. Work need not be the consideration for proof. Okay. So blockchain stuff. So 2 power 72 hash computations and all is meaningless for arbitrary applications. What happens is, okay, just a few newfangled ideas which are coming to this, and I think I'll stop this. These newfangled ideas how to use hash chains as data structuring mechanism together with proof mechanism, which is probably not necessarily this way. And once again, this for cryptography students who have done here, there is something called zero-knowledge interactive proofs, which is a nice thing, which is again invention of this stalwarts like Adi Shamir and Fiat Feiger, all the students in Israel and so on. It works something like this. See, for example, when you give your credit card number or give your password for getting authenticated, what do? You type the password. And what happens? This password is not sent in the clear on the line. That's where it should be. it should be strong encrypted in your client. The encrypted thing should go there, somehow decrypted there, and its hash value or something which will be kept there. Even this value will not be kept, the hash value will be kept. So today what happens is all your login passwords, we give a password, the hash value, encrypted value or a hash value will be kept in the store, and then every time you give it, it's checked. So the server side, there is no storage of secrets, but on the transit, it's the clear. It should be the case. There's something called zero knowledge interactive proof. It roughly works like this. You are the verifier, I'm the prover. It's called the prover verifier model in complexity theory. I need to prove that I hold a secret. You need to verify that I have the secret. One way is to show the secret, you verify. Okay, as simple as that. But that's not on. What is done in this is I make a commitment to the fact that I own a secret. Now, this ownership for anything. I own 10,000 rupees. So if you got all the smart contracts and all that, it's going to be useful. I will tell you, I got 10,000 rupees, you sell me this. You show me the product. You say, okay, see the product. Then I say, give it. Now you will say, give me the money. No, I say, you do it first. Now imagine this dialogue goes on in the ephemeral digital world. Here we can resolve it. In that world it is different. So who does something first should be tacitly safe, secure. So one of the ways is, if I have 10,000 rupees or a password, I make a commitment to that effect. These are called public commitments. Then the rest of it is simple. There is something called a challenge response mechanism, which operates in the classical world, in military and all that. But in modern world, in your examination world, the fact that you know about data structures and algorithms, how do I test? I give you a challenge, a question, you answer the question. If the question meets my requirement, you get marks. Same way, with an addition, that commitment, because now I have 10,000, I will put a commitment, ABCDY. You will ask a challenge. You will say, if you seem to have 10,000 and that thing is computed with this, I will give you this, you give me an answer. And I won't know what you will challenge me with. What I will do is, I will give you a response. You will ask me some 7, 8, 4, 5, 6. I will give you 3, 4, 9, 3, 2. But this 3, 4, 9, 3, 2 will be computed with my commitment and my secret. And what you will do is, you will use my commitment and this response, and then the cryptography will assure that indeed, only the person who had that could have computed it. Anyone else can compute something, because it all goes on in public channels. But you will probabilistically, you can be right or wrong only, even 50.5 probability. So the challenge response is repeated 20 times, 30 times to amplify your certainty. This is a simple idea as an analogy, but affected by means of nice discrete log and RSA type of integer factoring type of paradigms, and a few other number theoretic paradigms. Now, a new cash system has come already. So like the startup world, everybody jumps into some new startup. So these are all some new coins, Pinocchio. So I was telling us Zero Coin, there's a new system which is coming up, the open network, and they call the coin the gram, a telegram, gram. Raising money should be easy for Telegram. Shutting out the state will be far more testing. So this is the economist comment on saying, see, governments are very unclear about what these new animals are. So if somebody raises what is called as an initial coin offering with a new coin, then nothing wrong. But people there get worried, what are you going to use it for? If there is so much privacy, so much this thing, will you use it for guns, or will you use it for the war, terrorist funding, all kinds. Okay, I think last comment, it's important. There is something about this proof of work. Okay, now this is a whimsical comment, I thought, but then there is a seriousness to this in some literature of the books which are cited, particularly one on Bitcoin. See, this 272 coins computing and the enormous amount of power and things like that, and somebody caused how much carbon footprint it leaves. It's all huge. It seems a big waste. Okay, because that the waste means the goal output is there. Some coin is minted, some reward is given. It may not be used for transactions, but all the work you get done in between is junk. It's waste. 2 to the 72 hash strings you are producing, all no 72 bit zero some junks. Those junk numbers are junk. One of the nice things is to do scientifically what I call this byword. I have this quirkiness of inventing acronyms and words and phrases and poems. SUPW, you all heard of it at school, socially useful and productive work. So I call it scientifically useful and productive work. And all of you have heard of what are called as public sourced scientific work. This LHC, Large Hadron Collider, data processing, SETI, search for extraterrestrial intelligence, and some cryptanalysis problems, LIGO, satellite data, proteomics, crowdsourcing. What you can do is, provided I know I need to look for 2 to the 72 computations before I get it. And there's no way I can cut it short. Maybe a factor of 1 or 2, it doesn't matter. In fact, some of these things will come out with a probability one a little bit skewed that way, means 2 to the 71. Okay, not much more different. So if you're hunting for species of stuff hidden somewhere in a vast amount of data which needs to be crunched, you can feed that to the Bitcoin mining rig. Use this as a proof of work. So you're doing, every time you are doing, instead of doing junk work, you do some useful work. So at the end of 2 to the 71, anyway, you will get a useful answer, and that's the idea. So this is a very fascinating challenge to set up. I'm thinking of some number theoretic problems which are like that, which can do. So this is the idea, and but there is this coin-based stuff which we have done some work, and we had recently published this as well. And I'll just stop now with just some generic references. Yeah, so the last thing I just wanted to say, a little advertisement, and there is some excitement in other startup, this company. So I was telling them we will make but Zcash, Zero Cash was there. So now we make a Zero Coin, ZIROH coin, Zero Coin. You might see this, but if I want to see if it's a fiat currency or something like that. See, it's an interesting paradigm this company is doing, distributed storage and computed services for which you pay. Eventual cloud in which services are offered, somebody pays. Now more and more, the digital economy with digital goods and services, with digital instruments of money are important. Okay, so e-commerce is one where physical goods with digital money transactions are made, and or digital goods with digital, or the movies and videos and downloads and all that. Similarly, if you have cloud services in which database services, compute services are offered somewhere, and you need to pay to use it, so this company is telling to make a case for that. So this is the last pitch, and then I stop. Okay, with a whimsical take finally, just one serious references. Just as I said, this early book on Bitcoins is good. Anthropoulos is also well cited. Contrary to academic textbooks, these early books on both subjects are really good. And similarly, the blockchain, for example, Melanie Swain's, it's also early. And then some recent publications we put together. Okay. Lastly, a small description of the whole of this, what I said, was sequences of chunks of cryptocurrencies and blockchains, or the ledgers of nucleates of blocks from many terrains, of fiscal, transactional, and ubiquitous informational data. These new age chants of business and government, etc., need for demystification the academic computational reference like this meeting. Thank you. We can take a few questions at 4 o'clock, I think, is the limit. Yeah.
How the order of the value transaction is maintained in a permission blockchain?
See, permission blockchain. See, all these have the trappings of digital signatures. Here, the digital signatures are used for masking the identities and something. The permission blockchains, I suppose, every block will be signed with the private key of the that consortium or that user group. So it may not be at every transaction level, maybe at a block level.
My question is like, if at the simultaneous, like T1 and T2 transactions are performed and both are valid. So like putting into the blockchain that transaction, the order will get, I mean, does it T1 T2 or T2 T1? In permission.
You mean same data, same everything?
Yeah, two different miners, I mean.
Oh, wait. See, the two different miners and then the consensus is arrived by some distributed computing paradigm, right? What should be put is only one. If two people arrive at something, proofs, whichever comes first or something like that is the agreement.
Possibility both came at the same time, so which order?
Yeah, see, this part of the distributed consensus agreement mechanisms are outside the purview of the crypto, because that could have been there in any database update also. Distributed database updates. If concurrently two people update a database, somewhere there are resolution mechanisms, right? Here, that has nothing to do with that, no? The crypto proof, see, two pieces of data arrive. Which one to put into something before chaining is a judgment. As per any other data, it's the same thing. I don't know, maybe we have not understood the exact problem, we can discuss it later.
So miners will make this decision.
See, okay, now that's what miners means in the distributed consensus protocols, whatever operates in that system will decide. If it is majority or something like that, or time synchronized stuff, the first one to arrive and so on. And there are, even for Bitcoin mining, there are some discussions of this kind where sometimes, there is kept in a buffer because things will arrive at different places for different things also. So there is something about some buffering of something for some time, and then take the larger of the chain, which has a longer one as a more valid or something like that. Some resolution mechanism is.
How is zero proof of what working actually? Because this is not a practice. Suppose I don't know about any, don't ask any question to you and you just answering me and know yes, you have a this is difficult. So it's what?
No, see, zero knowledge, okay. Zero knowledge proofs, interactive proof, it's a proof system. Prover and verifier will exchange. Interactive because they have to exchange challenge response. The zero knowledge has nothing to do with zero knowledge has to do with the fact that only one bit is finally known. That I have the secret. Okay. So the zero knowledge has nothing to do with the having to know the secret. It's not needed. See, I'm saying password. Why should the server know your password? You tell me. It should know that you have the password, or the person at the other end who has typed from this client password and his name matches. But for that, the password need not be revealed.
How can you trust them actually?
See, you have to now trust the discrete log algorithm on which this modular experimentation in certain groups are done. So the answer can be arrived at if and only if the private key is known. Like public key, private key pairs which are used. There is a private key which I keep, public key is public. So anything you sign with this can be verified with the public key. And that's a proof that I have the private key. That's all. That's the simplest way. But that's a bit expensive. These are cheaper, quicker. One type that I'm not at the time. But to preclude the possibility of somebody mimicking something, this is called man in the middle kind of attacks. They tried it multiple number of times. That's the idea. At the end of it, you still don't reveal anything about the proof. Okay. Okay. Yeah.
Bitcoin is quite volatile. So what happens if there's a huge variation in the value of Bitcoin from the time you send it and the time you receive it?
No, I'm. This is outside the purview of the because 70,000 becomes 11,000. What is the meaning? There's no meaning. But they also say there is no meaning in many stock value predictions also. Say stock of some company goes up. You invest some money, you get some returns. It depends on when you buy and when you sell. You can make or lose money. So, but that goes within boundaries, and there are some other principles of economics which operate. That stock is invested in some productive thing, which I know the productivity rate, so it might yield and all that. Here, all that is not understood. So that's what the finance people are worried about. So once people start accepting, if Bitcoin is used for a startup company, you take money with Bitcoin. See, there is another big problem. Bitcoin, now there is a hardness of conversion from cryptocurrency to fiat currency. See, from fiat currency to cryptocurrency you can convert. How will you buy Bitcoin? You and I, anybody can buy on the internet. So we give our credit card number, it will be back debited. So to that extent, there's no question of legality or anything. It's like any other commodity. Any commodity in the world, you can buy Bitcoin, like a book from Amazon. But when you want to return the Bitcoin, you will not get money. I believe it's getting difficult. Okay. 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 Are there any other?